Welcome to this lecture series in linear algebra. In this lecture, we will be defining dual spaces, and pretty much that is what we will do. It is going to be a very short lecture. So let us recap what we need. So previously, we have seen why the dimension of the set of all the linear maps from a vector space to another vector space is the product of the dimensions of the participating spaces. All right, so how did this come about? We need to know the details. Fix two vector spaces V and W and two bases arbitrarily. B is a basis for V and C is a basis for W. Then once you choose an index I, meaning you choose basically a Vi and a Wj, you can define a linear map from V to W just by prescribing it on the basis vectors of V. What does this guy do? It sends Vi to Wj but kills every other basis vector. So it's a very simple recipe, and if you collect all the Tij's, they form a basis for this space, and therefore the dimension of this space is this number. So we saw this, and this is what we will use at one point. In fact, we will use a very simple version of this at one point. Alright, so let us move on. Here is one problem for practice. And now let us get started. So fix a vector space V over some field F. We define a linear functional on V as a linear map from V to F. So again, recall, S can be thought of as a vector space over itself, and therefore it makes sense to ask for linear maps from V to F. And any such linear map is called a linear functional on V. It's a very, very simple and straightforward definition, but it is going to be a very, very useful concept. All right, so let us look at some examples. So define this map phi from R2 to R, where of course we are thinking of R2 as a real vector space. So we define this map as takes an element of R2 and produces, let's say, this guy. This is of course for all. So you can easily verify that phi is linear and hence it is a linear functional. And you may want to depict the kernel of phi via a picture. So that is an exercise that you might want to do. All right, but you can generalize this example to complete generality, in fact. In some sense, it is complete generality. So you take this particular vector space, you fix a positive integer n, and we have this vector space. And then you fix some elements of the base field, not just some elements, n elements. N is this number that you've chosen. So you fix n elements of the base field, and then you can define this map from this vector space to F as phi of this particular thing. This is a vector in F to the n as the following element of F. Of course, for all elements of F to the n. So again, this is linear. Phi is linear, and therefore we have a linear functional on F to the n. And yeah, maybe I should say this at this point. These are all the linear functionals on F to the n. So if you have a linear functional on F to the n, you will be able to find some such alpha i's such that this happens. You can think about it, but we will prove it shortly in a somewhat indirect fashion maybe. I hope I don't forget to give a proof of it. All right, so here is a notation. The set of all the linear functionals on a vector space is denoted by this symbol V, and then we decorate it with a star on top. Just a notation. So this is the set of all the linear functionals on V, and of course this is also same as, by definition, this is same as that. This is the set of all the linear maps from V to F, but as we know, this itself is a vector space. the set of all the linear maps from a vector space to another forms a vector space in a natural way. So this is a vector space, and hence V star itself is a vector space. Yeah. So V star itself is a vector space over the base field F, of course. So out of the vector space V, we have created another vector space. Okay. And this is a corollary of what we know. The dimension of this space is dimension of V times dimension of F. But the dimension of F is 1. So the dimension of this is just the same as the dimension of V. And hence dimension of V star is same as dimension of V. So this immediately follows. So these are just some concepts. Unclear as of now why this is useful. And in this lecture, we will not be able to illustrate as to why this is useful. But anyway, so let me introduce the notion of a dual basis. Fix a vector space over some field F and fix a basis of our vector space. Then we define the dual basis of B. We define the dual basis of B as so before I write the statement, maybe I should. So we will come to this, but define, so fix some I in this range 1 up to n. We define this thing Vi star as a map from V to, as a map from, or rather let me say Vi star as an element of V star. So it is a linear map from V to F via this equation, by writing something. So we want to define a linear map from V to F. So we may just describe what it does, what this guy does to each basis vector, and that will uniquely define a linear map. So by writing this, Vi star of Vj, this is equal to 1 if I equals j and 0 otherwise. So that's the definition of Vi star. It is a linear map which does this. It takes Vi to 1 and kills everything else. So that is our definition. And if you were, if you looked at the recap that we did in the beginning, you can immediately say that this thing is a basis of V star, which is of course Hom V, F. This is immediate from the recall, and this is called the dual basis. So this thing is called the dual basis of B. So this will be a useful concept. Again, as of now, it is unclear why these things are useful. And and I wanted to comment on as to why these are all linear functionals. So I will probably leave this as an exercise, but let me hint at a proof of it. We already know that the dimension of V star is, or dimension of the dual of this space is n, because the dimension of this space is n. And now for each element, for each choice of n things in the scalar, in the base field, you get a linear functional. So for each element of f to the n, once you choose these things, you get an element of f to the n, basically, just put it in a tuple. So for each element of f to the n, you get an element of fn star, right? Once you choose alpha 1 up to alpha n, you get a phi. So once you choose alpha 1 up to alpha n, you get a phi. So you get a map from fn to fn star, and you will see that this map is linear, and its kernel will be 0, hence this will be a linear isomorphism. And therefore this will be bijective, and therefore every linear functional will find such alpha 1 up to alpha n. So that's the reason, and maybe I will leave that as an exercise. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.